Awesome, cool. All right, actually, first of all, thanks so much for coming. I have the worst time for the session, so I'm so grateful that you guys make it. I know I'm sitting between you and the pints, so hopefully it will be worth your time. I'm a technical evangelist, actually software engineer, part of the technical evangelist team at AWS. I specialize mostly in distributed systems, resiliency, work quite much with our reliability team at Amazon and AWS, working at trying to figure out how do we scale systems. And if you look at the history a little bit of system, this is just to give you an idea of what we're dealing with. When we started Amazon back in the days in 1994, it was a big Java monolith application, and we went into splitting that into a set of microservices. In fact, there's about 1,500 something microservices that serves the Amazon.com website today. No one really knows the number of microservices. It goes up and down regularly. Twitter, Netflix, very similar, right? So there's tons of microservices everywhere. In fact, this is the extreme, right? But what we say is, if you give an architect about 10 different microservices, it becomes very, very difficult for him already trying to make sense of it, how things work. Actually, we say that about 3 or 4 systems is enough to create big confusion in the minds, right? And most of the service we build nowadays actually have more than 4, 5 systems, right? So we easily go into the realm of complex systems. And when we go in the realm of complex systems, in systems with hundreds or thousands of microservices, it's actually very normal to have, at any given time, many of those services that don't work or that fail, right? And we call that partial failure mode. This is a representation of what partial failure mode means when you run that in production. This is actually in India, and they do a tire repair while the mob is still running. And this is actually a working system, right? It still moves forward, it carries people, it just has a little problem, right? Which is being fixed in production. And this is exactly how we run large-scale software systems. All the time, things fail, right? So we always have to deal with those failures at any given moment. So why I'm telling you this? I'm telling you this because actually resiliency is exactly that art. It's the art of being able to run system with failures, right? And especially how to go around conditions where you can't predict, right? Especially how do you deal with unexpected conditions? How do you recover from them, and how do you move forward? So this talk actually is about some of the patterns we've seen through our customers, some of the patterns we use at AWS to build services for you. Right? So there's a bunch of those that I will discuss and show you how we build a software system that scales to millions. Some of them are very simple. Some of them are genius, in my opinion, but more because they are simple. Right? I think a lot of the time, people think about large-scale system as being very complicated. Actually, if you can simplify them, usually that's what is genius. This talk wouldn't have been possible with all the principal engineers that work in Amazon. There's hundreds of those. We often run talks inside Amazon to discuss how we build stuff, to share cultures. Many of those ideas don't come from me directly, come from the folks that actually been working at Amazon and for the last 20 years. So I just want to call out some of my favorite of these ones, and especially that contribute a lot about how Amazon works. And they're on Twitter, especially Colm always has very interesting stories on Twitter, so I highly recommend to go follow that guy. Before I go into discussing those patterns, I'll give you 10 of those, and you might want to take them home and try to implement. But actually, even implementing them doesn't necessarily solve all the problem. What we figured out is actually the most important thing is the habit, right? Is how do you build habits within your team to actually build quality software. It goes from writing code to code review to thinking about the overall system, right? So actually building that habit, a quality habit, is often more important than trying to implement a particular pattern. Those patterns are good as a direction to go, but don't forget that actually to implement a good pattern and to make it sustainable, you need to have all the ecosystems around, okay? So we're gonna review 10 of those. Before I dwell into the first one, I want to remind you the famous 9s of availability. I think when we talk about resiliency and when we talk about software, it's super important to remember what it means. Actually, in the industry, it's very common nowadays to claim that we have 4 or 5 9s of availability. That means actually you are in between 50 minutes to 5 minutes of downtime a year, which is ridiculous in terms of availability. It's very, very good. In practice, very, very hard to implement. Right? In fact, I can tell you some of the outage I've lived 7 years ago. Our escalation path actually failed while we had a cascading failure inside the system, so it was a double failure. And it took 27 minutes for us to notice that there was a cascading failure in the system. In fact, it was a customer that did call us and say, your system is not working. Actually, the escalation path had failed as well. So it was, we had already blown half of the credits for our 4 9s of availability. All right, so at the end of the day, remember that value, and when you design system, be humble with them because they'll catch you back very fast. And one of the things I want to talk about availability is actually related to mathematics. This equation, and it's the equation of parallel systems. And it's an equation that actually is at the heart of everything which is happening in the cloud most of the time when you talk about duplicating workloads. If you take a part and you give it like 99% of availability, which is really, really bad, because it means that particular part is able to be down for about 3 days, 15 hours a year. That's a lot. Your customers are not going to be happy if you give them this kind of availability. But if you take that component and actually you don't do anything else, but you duplicate it, you make it redundant, you all of a sudden increase it to 52 minutes downtime a year. So it's a dramatic reduction. If you make it 3 times, you actually go straight away to 6 9s of availability. And actually, these ideas of duplicating is at the heart of every service we built. Right? Actually, S3, availability, durability, is all based on this kind of redundancy. And it's also at the heart of how we build our regions. So we have about 19 different geographic regions on AWS. And I want to tell you a little bit how we build a region because it's very related to mathematics. A region is a set of data centers. And those data centers are grouped in what we call availability zones. So if you use AWS, you often see availability zone A, B, C, D. In fact, just a pro tip, if you see availability in US 1A and you say 1A, it doesn't mean it's the same availability under the hood, right? We actually switch those for resiliency purposes, right? Because people would tend to select always the 1A or 2B. So if we actually make them random under the hood, we increase the distribution of customers across those availability zones. But those AZs, they are geographically separated. In fact, they are separated by a few kilometers, usually 1 or 2 millisecond latency. And this is so that we can do synchronous replications between these AZs, right? So we have a region split with 3 or more AZs. Some of the big regions have 7 AZs. An AZ is actually a unit of capacity. We usually tend to limit our AZ to a certain capacity. If we need to increase that, we build another AZ. Right? And it's the same. One AZ can be one data center up to several data centers. Right? And our data centers, we usually limit them to 50,000 servers, something like this. So AZs, which are all the oldest AZs, have a lot of data centers in them, right? Sometimes up to 10 or more. So this is very important. And each of those AZs are actually linked by very high-speed network so that we can actually do very good networking, high-speed networking and replication. Now, the first patterns that we use actually, that also we recommend all our customers to use is when you build application is actually leverage that. Because by leveraging the 3 AZs like this, you can use the mathematics of redundancy, right? So if you have an application and it's only 1 AZ, then your availability is usually not very good. Especially its blast radius is quite high. So we always say to our customers, and we also do inside for building services for you, that we actually deploy our application across multiple AZs. So this is the first patterns we do. Very often, we often use a database which is synchronously replicated across several AZs so that if there is an AZ that goes down, actually we can implement a failover to the other region, and the application will keep working. And this is a very simple pattern, right? Simply relying on mathematics. Now, if you take that, it's very good for fault tolerance, right? Because if one AZs go down, well, the other AZs will take over. Right? So most of our regional service, like DynamoDB, S3, or the ELBs, actually leverage this kind of stuff, right? So under the hood, we also implement services like this. And this is also dictating the kind of service we're offering. If you use AWS, you probably have noticed that we have regional services like S3, DynamoDB. You can't decide which AZs they are, right? By default, they will be spreading data and load across all those AZs. But we also have what we call zonal services, which are actually very dependent on the availability zone in which you launch them, like an instance, right? You have to choose the AZ. So the kind of zonal service can't benefit from this kind of multi-AZ architectures. So what do we do with this? So if you look at the availability, and especially the blast radius of these kind of things, for zonal services, our blast radius is actually usually 1 AZ. So if we have a zonal service and one particular AZ is experiencing issues, that all AZs will kind of go down, but the other services will be able to recover, right, if you use regional services. Now, if you have instances in this particular zone and it experiences issue, you can't recover from it. Right? So this is kind of the blast radius in that case for zonal service is actually quite big. Now, the theoretical blast radius for actually regional services is the biggest, right? So if we have regional services that goes down, the top layer, which actually routes the traffic between different AZs, if this is experiencing issue, theoretically, we could have regional failures. In fact, in 2007, we had an ELB data plane experiencing issues that took actually some of the traffic out in the entire region. Right? So the theoretical blast radius is pretty high. Now, if you think a little bit about how boats are constructed, they implement what we call compartments, right? Bulkheads. And those bulkheads are actually very useful. It didn't really work out for Titanic, but it could have. But imagine you actually have a hole in the boat. The water will fill only one part of that compartment. And eventually, all those compartments are actually waterproof, right? Or the water won't go into the other compartments, so the boat will be resilient to, let's say, a hole in part of the boats. And this has been implemented from the very early days of navigation. And if you take that idea, you can actually use it into the cloud. And at AWS, how we build our service, we use something called sail-based architectures. A sail is, let's take a service, for example, an application that is deployed across multiple AZs. We call that we take that application and we move this in what we call a sale, right? So I reduce it a little bit for clarity. And what we do is we duplicate that sale. So instead of having one application, actually, we have multiple applications compartmented in sales with a very, very thin routing layer. Right? Actually, that routing layer has as little as possible, right? And tries to do it as fast as possible. In fact, that sales routing layer is also implementing what we call sale architecture, so that in case of zonal failure, actually the sale router will stay up. And this is deployed in what we call a regional service. So now, if you think about sales and the availability zone, and you think about blast radius, actually, if you have a regional service initially having an issue in a sale-based architecture, you actually are able to be resilient, because now, instead of having one big regional service, you have multiple sales that serve that service. And for us, we build all our services like this. So most of that kind of architectures, you can also implement that actually using DNS. So for example, if you make a request to Route 53, you can compartment that, within a cell, and then allocate some of those users to these kind of different cells. So this is very easy to implement as well. So these services allow you to implement kind of resiliency on both regional and zonal level, okay? And of course, it also allows you to have resiliency to partial failures, because now you have multiple sales for each of the oases. So if one cell is experiencing issues, the other cells are not affected because they are like bulkhead. They are not, they don't have any relations to each other. Now the system property is very interesting because, of course, you have workload isolation, right? You have failure compartmentalization, so that if you have a failure in one of those cells, it doesn't propagate to the others. The other ones still stay up and running. But these cells actually for us are really interesting for another dimension, for scaling up. Actually, instead of scaling up in terms of power or instance, or what we call scaling up, we scale out. Right? So we take a cell and we say, okay, that cell will have a maximum number of users, we'll have a maximum number of servers, and then if this increases, we'll add other cells. And actually, some of the biggest services have thousands of cells, right? So this is actually very interesting for us because now those cells allow us to also do rollout, right? While limiting the blast radius, because now we can roll out per cells, and we can notice if there are issues in each of the cells. If there are issues, we can roll back easily. The blast radius is contained, like is minimum. We also actually do what we call chaos engineering in those cells, so that we can test in real production data how things really behave. So that means we are able to understand a system within the cell and then replicate that into other cells, right? Because we always have a maximum capacity for a cell. Once we understand it very well, we can replicate that learning from one cell to the others. Right? So this is very interesting for us in terms of testability and manageability. And of course, when you want to understand how a system behaves, it's a lot easier to have a smaller cell and try to dig in into how the system behaves within that cells, which maybe has 1,000 people and 1,000 servers versus a cell which has 10,000 servers and millions of people. So the logs, all these kind of things is much more manageable. So this is very important for us. Now there's another pattern that is very interesting is, let's take, for example, an application. And if I have an application and I have 8 different users, right? So each of the icons is a particular user. Now say my user, one of the users is experiencing issues, or for example, he makes a query that damages the backend. These kind of expensive queries which hit the particular bug, which actually take down things very easily? Well, what often it will do, this request will hit one server, right? The server will go down because it was a very expensive request that happens very easily. Now the user usually has a retry, right? So we will eventually retry and actually take down all the other servers. And these conditions are very common, and they are maximizing the blast radius to pretty much all the servers, right? So the blast radius is affecting all the customers here. So all the customers will suffer from one particular request that one user has made. And this is very common. That's what we call cascading failures. Cascading failures representing, I think is very easy to understand cascading failure when you look at this map. If you think about having a load balancing load between two servers, she hits a condition where one of the servers is unstable, and then moves all our attention to the other server, creating overload and taking it down as well. And this is exactly what these conditions happen. It doesn't have to be big problems on the instance. Sometimes really just a particular bug, a query, the way a condition that you haven't tested can degenerate very easily and take whole clusters down in matters of minutes. So to prevent these kind of things, we also we implement these kind of cell-based architectures as well for our customers. So instead of having now all the customers being able to utilize a cluster of instance, what we do is we compartmentalize this cluster into cells, and we assign, for example, a cell to the same user, and this time the blast radius is actually going to be only one user affected. Right? So the other are not going to be affected by that particular dangerous query. So this is something that we do for all our services, right? So to limit the blast radius. And in that case, actually, the blast radius all of a sudden becomes 25% instead of 100%. So we have a factor 4 of improvement. But that's actually not all. You can do a lot better. And this takes me to the third pattern that we really like at AWS, what we call shuffle sharding. Shuffle sharding is very simple. Instead of allocating a user to the entire set of cluster or to a cell, we actually randomize a user for a particular instance. And actually, we assign this user to 2 particular instances in that case. And then all other users we also randomize. But what you realize is actually by doing this, now if I have an expensive query about the same user, the blast radius, of course, will take down the servers here. But the same users now, the heart, will just make a retry and will be able to have a successful request to the other servers. And actually, in that case, it's very interesting because our blast radius is now the number of customers divided by the combinations of that we have done the shuffling, right? So in that case, if you have 8 nodes and you have a shard size of 2, your percentage of, or your blast radius is 3.6%. So we went from 125 to 3.6%. And it's quite interesting because you only had 8 nodes, and your combination is already 28 different combinations, right? So if you have thousands of those nodes, the blast radius goes close to 0.something%. So this is a very, very useful patterns that you can also use to do that. Again, we do the shuffling based on particular hash, which assign 2 servers to that particular users, and then randomize the rest. It's kind of random, kind of not. This hash is actually, depending on the service, can vary, but you can think of it as a random shuffling. And this is the mathematical equation behind. So something very interesting. And what it does is actually, this is actually the number of for 100 of nodes, the number of combination is 75 million. Therefore, your blast radius is close to nothing, really. So shuffle sharding is very interesting because it gives us a very minimal blast radius. The only thing it requires, very simple, it just requires a client to do retry, because if one request fails, then it will have to retry that particular request to another server. It works for a lot of different things, like servers, queues, or asynchronous systems. We actually use it at many, many different places, both from the Route 53 to S3 to DynamoDB, different services to be able to distribute the loads. And of course, you need a routing mechanism, which you have. Okay. So this is a very interesting one. Now you've probably all heard about autoscaling, and autoscaling is mostly known for being able to adapt an infrastructure to the load that it receives, right? So for example, you have maybe a peak traffic during daytime, and then all your traffic goes very low during the night. So you bring up resources during the day and then shut them down automatically during the night. And this is a very common way of autoscaling. But actually, in my opinion, it's not the best way of it. What is very interesting with autoscaling is that you can assign a minimum resource, right? So for example, in that case, it's just an example. If I have 2 servers distributed across 2 AZs, and I set a minimum of instances superior to 0, by default, the system will self-heal. So if actually one of the instances go down, automatically the load balancer will take it out of the application and will terminate it and then automatically come back out. And this is, in my opinion, very interesting, a very simple thing to do, like the basic of self-healing systems, right? And then eventually the load balancer will do some health check, figure out that this is a new instance, so we'll bring it back up inside the load balancer autoscaling group. Even though this feature has been out for about 6 years, it's still very common that customers don't know about it. So I think this is very important that you know. And actually, we do use that pattern extensively inside AWS and Amazon as well. This is an accelerated video of how this works. So this, I have a load balancer which has instances. I kill an instance. And here you see the system terminates that instance. You'll see it's shutting down here. And the system realizes that actually one of the instances is going down, and automatically will bring that instance, a new instance back up. And this really happens in a matter of minutes. So very interesting features that you need to leverage. You see it's automatically launching a new one. So very simple, and yet very, very, very useful. The Pattem 5 is about decoupling decoupling services from each other. I think it's been very common back in the day to have synchronous systems where you make a query, you wait for the query to execute, and then come back when that query has been executed. Now the problem is if my process B doesn't respond in time or is slow, my process A will suffer. So you have coupling of processes or services, and this is terrible. Right? So we move extensively to asynchronous patterns, and actually most of the back-end framework and front-end framework do support this kind of patterns. But what we really, really like, and what I suggest you should think of, is actually decoupling what we call the API layer from the business logic. If you look at sets of API in an application, I think very often many of those don't need to be synchronous. Very, very few need to be synchronous. Like, for example, bank transactions. You probably want that to be synchronous and make sure that that transaction happened. But most of the other, you can do it asynchronously. It doesn't mean that you show it as an asynchronous request to the end user. You can hide the asynchronicity in the UI, make it look like hey, it's synchronous. That's what all Instagram, Facebook, and all applications where you upload videos do. But you need to do this because it allows you to do very interesting things. For example, you see in that case, I have an API, and I assign it a job ID in that case, and I return immediately. Now that job, of course, goes in a queue. Most of the asynchronous patterns in the cloud are using queues. So you put that job in the queue, and then you have kind of a group of worker instances or that implement business logic that take that job and execute it. Now you might think that actually it's slower because you have now 3 parts, but it's actually very often as fast as synchronous operation because you can scale both clusters from independent from one another. For example, worker instances are often CPU intensive, whereas API instances are more memory intensive because you have to open WebSockets and things. You have to open network sockets which take memories, and then after a particular load, it kind of has a massive effect on how your instances behave. But this is very interesting. So your worker instance takes the job from the queue, and then once they have executed the job, just store that in a cache, and then you can actually send a notification to the end user, say, oh, your result is available, come and fetch it, this is cool. And this pattern is used extensively all over the place. What I really like about this pattern is actually that you can implement degradations and prioritizations. So now imagine your backend or your applications or service is experiencing a slowdown. A very common practice is actually to do request cancellation. And so the service is down, we can't take requests, so try later. And you see this all over the place. Now you can actually take the idea of, okay, what are the APIs? What are the functions in my application which can be prioritized versus the others, right? And then you can take that idea of prioritization and actually build several queues, like high priority queue, low priority, do it when you can kind of queue. So you can actually scale the queue in terms of priorities and then do service degradation. So for example, instead of saying, oh, you can't access Netflix because the authentication system doesn't work, you'll say, okay, I'm going to degrade, and I'm going to go into an open systems, but still handle API calls that do start videos or things like this. And then under the hood, start fixing the backend. In fact, many of the services we build as well are based on this kind of pattern. So we try to understand what are the APIs that are really important and how we want to prioritize those APIs in case of failures. Right? And this is very interesting. Now, I want to talk a little bit about timeouts and retry because in these systems, it's very important to have them in place. So let's take a simple example of users connecting to an application that connects to a backend, okay? Now, that makes queries to a database. Now, imagine that database at some point starts to slow down. So what happens? Well, what happens, actually? It's a very interesting question. There's tons of things can happen, right? But we're talking about retries and timeouts. So first thing that you have to figure out is actually what are the timeouts involved, right? So you look at the timeouts on the client side, you look at the timeouts on the backend side, and very often, if you ask teams, it's the first question mark is, oh, I'm not sure, actually. The default. Okay, default. So let's go with default, okay? Let's have a user, one, make a query to the app. That app make an insert to database. That database slows down. Well, my insert slows down, right? Eventually, if I have a timeout of 10 seconds, but my insert has a default timeout, well, you don't know when what's going to happen. Basically, eventually, this one will time out or not. If your timeout is 20, 30, 1 minute, or infinite, this connection will stay open, and actually the client will time out and make a retry. Right? So my client makes a retry. My connection is still open to the database. I make another retry, another insert, same behavior. My query slows down, doesn't time out. My client retries and retries. And you see, at some point, you'll have something like this. Right? So how many of you have seen that message, right? Failed to get connection from pools. Right? So that means you've exhausted the number of connections available to your database, and now actually your users cannot even make requests to the application. And this is actually a very, very common pattern to having cascading failures, because actually that user then will do a retry. The application cannot be contacted, so the load balancer will push that to another servers, and the same patterns will happen. Actually, I've seen 120 database servers go down in literally less than 30 minutes because of that. So this is very, very dangerous pattern. Now you might be wondering, why did the hell I put a timeout of infinite? Well, actually, how many of you are Python developers here? Yeah? How many of you know the JDBC drivers for NoSQL? Timeouts. Anyone want to take a guess what kind of timeouts we have for most of the actually language and defaults? Well, actually, it's infinite. You'll be scared to actually look at documentation. Request timeout is the most used library for Python to do requests. Default, infinite. NoSQL, default, 0, which means infinite. Right. Actually, 80% of the frameworks I've used usually have a default timeout of zeros. And actually, if you go to customers and you are in software teams, most of the time, people don't know. That's actually a big, big problem. And it's been responsible for many, many outages that I've experienced. So in Python, you would do something like this. You put a decorator, and you do some retry. You say, let's do 5 retries. After 5 retries, you actually cancel the request. And cancellation is actually very, very good, something that should be implemented. You should never, ever have a client retry indefinitely. It's the best way to never recover from an outage. Right? Because then you have infinite number of customers making retries. Your system tries to come back up, goes down immediately after. So have a maximum number of timeouts, of retries, make them timeout, okay? So release them. But that's actually not it. There's another thing that could have been done to prevent that from happening. Well, retries are good, but actually, you should never retry immediately. Right? You should do what we call backoff. And there's several ways to do backoff. Backoff is, I'll make a request. If it fails, I'll wait, for example, 2 seconds and do a retry. If my request fails again, I'll try 4 seconds. If it fails again, I wait 8 seconds. We call that exponential backoff. Right? But actually, exponential backoff, again, is not necessarily the best. You see, the good thing with backoff here is that after 4 requests, if I have a timeout backend of 10 seconds, eventually it will start releasing database connections, right? So eventually your servers won't be so overloaded or won't start canceling requests. But that's not enough. Actually, there's a very interesting paper which we wrote about exponential backoff and how it behaves at large scale. And if you look at a classic backoff algorithm, which is simply exponential backoff, and you put it in kind of a distributed systems, eventually all the retries will still be clustered in kind of funnels, right? They will all have this kind of happen more or less at the same time. And this is very interesting. It's very interesting properties of exponential backoff in distributed systems is they actually are not random. Right? Most of the time, the retries will happen at the same time across the network and will synchronize. So what we figured out there's actually a very simple way to optimize exponential backoff is to add a jitter. So inside your sleep function, for example, you add actually a random or a jitter that kind of randomize a little bit your retry. And now, if you're Python, again, there are some interesting patterns that actually use that full jitter. There's a paper written about it. If you are interested, you should definitely read it because it's very, very interesting with all the math behind it. Now, of course, if you're doing retry, you have to use idempotent operations. Idempotent operations means that for any given retry, a request will always have the same behavior. But now it does have a problem, right? If I have a retry and if I have a request that writes to a database, my request actually can fail on the client side, on the backend side. How do I know in case of failures that actually the request has been executed? If you have independent operation, you might have 10 different inserts, and that will blow up your database as well. So you need to have a mechanism, for example, through a query hash. So you hash, or you try to identify queries. You hash a query to track it across its path and figuring out if it's been executed. So there's tons of operations to do at scale to be able to figure out is actually if a retry has been executed or not. And it's not a simple problem. It can make system quite complex. But it's something you have to take into consideration. So doing timeouts and retry is good. Doing idempotent operation is good. But make sure that actually operation doesn't blow up your database. So make sure that you can try, you can figure out if a request has been successful or not. So there's some different strategy. There's a bucket strategy, so where you put a token in a bucket for each request. If it's been successful, you remove it from the bucket. Interesting. If you're interested into that pattern, Google has tons of answer around that. Google search. And of course, in distributed system, there's another thing you need to work with. So if I have a client and I want to do retries, it's probably a good idea that my client has an idea of what's the condition of the network, right? So very often, distributed systems will have health checks. Right? We all have built health checks for our operations, for our systems. Now there's different type of health checks. There's like what we call the shallow health checks and the deep health check. So the shallow health check, in that case, if I have an issue in my application, say for example, the shallow health check will check the instance and say, yeah, my instance is up and running. I'm all good. Right? And actually, it will return all good even if, for example, an email server is down because it's a shallow. It doesn't go and check further down the stream. If you want to figure out further down the stream the conditions of the network, you have to implement deep health checks. Right? So for example, a health check that will propagate to all the other services, often asynchronously, figuring out their condition, come back to the instance and say, yep, everyone is up and running. You can pass it back. We're good. So when should you implement a deep health check and when should you do a shallow health check? Actually, very, very, very complicated question. Shallow health checks are very good for figuring out networking issues. Right? For example, say my instance is having security group networking issues, cannot access the database, or something like this, or that is resource constrained, doesn't have enough memory, doesn't have enough CPUs, so it doesn't answer my health check in time, start to time out. This is interesting. Now it's very bad for understanding the network condition. So, for example, shallow health check would have said my instance is healthy, and if you would have an API that asks to send an email, your email wouldn't have been sent, right, for example. Whereas a deep health check will check the condition of that email server and returns, are you healthy? Of course, I'm not healthy. Now you might also think, okay, but that's actually a problem, right? Because which service actually in the whole system are critical. Is actually an email server critical to your application? So that for a health check, you should say, no, I'm not healthy, so don't send me traffic, I cannot send emails. Well, no, right? So very often what you want to do is have a prioritizations of your system, figuring out, is it a critical service, is it not critical? What should I do if I have an email server going down? Should I actually report that I'm unhealthy, or should I just do an asynchronous call to a queue that will allow a work instance to take that job and send the job to an email server in case this is healthy, or when it goes back online, right? So that discussion needs to happen, right? It's not just straightforward to say, oh, I want to do a health check. You have to think carefully which one to use. Deep health checks are very good for when the system is running, when the cache has been warmed up, to figuring out if actually your application can do complex queries. But it's very bad at startup time. If our cache is not warmed up, or if downstream services take a bit longer to start, your instance is healthy, and then your deep health check will return not available because my cluster, for example, takes time to start. So actually, this is very important to do. So when you have an architecture and when you build microservices, try to build a map of critical services, how your API map to that service path, which calls should be asynchronous, because in that case, it would be very easy to say, oh, my email server is actually not critical. Instead of having a health check, I'll health check a queue, for example, say, oh, can I take the job of, and then make an asynchronous call to a queue and then send that to email servers. This should absolutely not be linked. And it might be trivial, but actually very, very often you see through health check couplings of services, which you don't necessarily think of. Right? So many of the problems have been fixed in the architectures I've seen in the last 15 years by doing this kind of very simple mapping of health check and how do they behave, are the service criticals or not. And this health check actually should not just be an information for instances in the cloud. Actually, you should bring back that information, especially information for deep health check. Bring it back to the clients, because they are very, very useful to do service degradation. So take the UI of Netflix, for example. And actually, when you scroll the UI, it's composed of many different, let's say, microservices that are powered by recommendation engines like Trending Now, or you've watched that movie, so you probably like this one, or this kind of things. Right? So there's about 150 services powering the UI of Netflix. If you have a deep health check that brings back kind of information about the condition of those critical service back to the UI, you are able to adapt the UI and make the UI not show errors, for example, right? So you can hide, you can say, okay, if my service that is recommending is not responding to a health check, well, actually, I'll just cancel it, right? But you can do something else as well. You can take that information from the deep health check and actually do fallbacks. And this is very interesting. For example, in that case, if my recommendation engine doesn't work, you would fall back to cache. Say, oh, popular on Netflix. Doesn't need any recommendation engine. It's simply a value, an array of IDs in cache, right? So the whole thing can be degraded simply because we have done a deep health check and then return that value into the UI. In fact, Amazon.com works like this as well. We'll collapse the UI, we'll do fallback in case of some of the services downstream not working properly or not returning the correct value. And it's also very interesting to spread load, right? If you start identifying clusters in sales that have, in our sales architectures, that has, let's say, degradations of service, we can actually start moving traffic around. So that leads me to pattern 8. Actually, very, very common. I'm sure all of you know that pattern is using circuit breaker, right? Which a circuit breaker is simply a way to decouple requests from one service to another, and you kind of wrap a request call inside an object. That object monitors the conditions of the downstream service that it wants to connect to. And if there's a lot of different timeouts going above a threshold, you break the circuit. Now, the interesting part with this is actually for developers, because if you use circuit breaker, it forces developers to think about fallback. You say, all right, when you create your object, you have the connection monitoring, that's fine, but your object needs a fallback. What do you do in case my circuit breaks? So this is why I really like that pattern. And now, database a little bit. Very classic patterns, database federation. It's a classic way of looking at spreading the load across different databases. It's very common in customers or especially that scale to never touch the database until the last moment because everyone is scared of database. And actually, every company I've worked with, it's always been like this. It's like everything was beautiful, and then the database, ooh, we can't touch that piece, right? So one of the simple patterns is actually database federation. When you look at queries, actually very often, you'll see that tables don't necessarily need to, or database don't necessarily, or tables don't need to be shared in the same database because there are no joins. So performance-wise, you actually can scale them independently. You might have users and product, and then have them scaled different ways. At Amazon in 2017, we actually analyzed as well the database queries that were happening on the platform, and 70% of them were not transactional. And guess what? We were using only transactional database. Right? That's crazy. This is why we started the whole Dynamo thing, right? DynamoDB was created simply because we actually realized that patterns were not transactional. Right? It was, we were trying to scale our transactional database, actually Oracle database back in the days, and we had massive problem with that because we were not using the database for what it's good for. Another way to do that, or to scale a little bit, is sharding, right? This is very common when you have global application. You shard your database per geography. So for example, you say, okay, all my users in Europe will go in a particular database or a particular table, and then you can split them. You can do federation after that. So this is very common pattern. But actually, very interesting patterns for resiliency is, and very simple, is read-write separation. And crazy enough, it's very rare that people implement that. So if you are using RDS or Aura or a transactional database, most of them support read replicas, right? So that means you can have a master database which replicate data synchronously or asynchronously to read replicas. So that means you can actually preserve your master for all the writes and then do the reads on the replicas. Of course, you are in the realm of eventual consistency because your master and your read replicas might not have exactly the same value for particular data, but it's a price to pay for having this kind of system, resilient system. And the interesting thing with this is actually you can fall back into read-only mode. So for example, take Amazon. Amazon.com business, or let's say Prime Video. Let's say this is how it's implemented. Prime Video business is actually to serve videos, right? If the database breaks, should we forbid everyone to watch videos because we couldn't fall back? No. So if the database master falls down, or if experiencing an issue, or if we have to maintain it, or if we have to change the schema or something like that, we actually fall back into read-only mode. And that's it. We suffer the consequences. For example, well, we won't be able to track some particular type of data at that time. But as a user, you can still consume. And this is the most important, right? So this is actually a very interesting pattern for degradation. And you should definitely think about it when you design an application. Now, continuing in the database, a very common pattern is actually to store transient state in database, like values of counters. I've seen this ridiculously amount of time. A counter which usually use an update queries. Update queries lock the table, so that means you cannot do writes on other fields, so that if you have a lot of users or if your database starts to slow down, you're going to have accumulation of update queries. Eventually, your database will go down, taking cascading failures, and boom, boom, boom. I've seen this happen all the time. So use the database for immutable data. If you have data that is going to be mutated in a minute, 2 minutes, 5 minutes, it should not be in the database. Because at scale, it's going to break. It's guaranteed. Especially for SQL and transactional database. So transient state, move that to NoSQL or in-memory store, like Redis or Memcache, something like this, especially in distributed system, but not transactional. For people, a very interesting pattern is think about firefighters, right? Firefighters take about 80% of their time to practice fighting fire in an experiment condition or in a test condition. So they go into a place, train, put fire, and then try to fight it. And really, pretty much 80% of the time, they do this. And you know why? Simply because they need to build what we call intuition, intuition for fighting fighter. If actually they don't use intuition, they will have to think too much, and it will be dead. So you have to take that pattern and actually think about it in terms of architectures and systems. At Amazon in 2017, we brought one firefighter to actually lead the resiliency team. He called Jesse Robbins. He was a firefighter and started to do what we call game days. Back in the day, game days was like, he was literally going around the data center, pulling out cables of stuff and figuring out what happens. Right? Of course, it was a contained environment. We really tried to reduce the blast radius. There's a legend that actually went into breaking a whole data center. The result was dramatic, but they learned a lot out of it. Right? And actually, this practice is still used today. We do game days all the time. Every time we launch a new region, we actually spend weeks and weeks breaking things in figuring out if the system is going to be resilient. Netflix called that chaos engineering, right? You all know chaos engineering because of the Chaos Monkey. Netflix started to do Chaos Monkey back in the days when they started to replicate their application across multiple regions and having very complex architectures. They needed to start breaking things randomly to see how the system was behaving. And actually, they realized, and you don't necessarily start with production environment. Right? So don't go Monday and say, oh, Adrian said we should do chaos engineering. Let's break the database in production. No, start in a test environment, build confidence into the system, figure out if you have the right patterns, if all those patterns have been implemented, if you've thought about it, if your timeouts are correct, if your retries are correct. This is the only place where you can actually do real tests, is production eventually. And this is why all those patterns are interesting, multi-AZs, sales, because you can have live traffic, which has a very limited blast radius. You can figure out where to do this. Of course, doing A/B testing or canary deployments is very important for that as well. So try to experiment with chaos engineering. Chaos engineering, you need to figure out this steady state of the environment, then make a hypothesis and say, oh, how is my system going to behave if I remove a database? If you ask all the software engineer in the company, often everyone will give a different answer. The UI will say something, the UI designer will say something, the database guy will say something, the backend guy will say something, the manager will say something. That's actually very interesting data, is why is everyone having a different answer? Right? And then take that data, that's enough to start with. And then once everyone has the same answer, then go and test it out. Check your hypothesis and say, oh, actually, is the system really going into read-only mode? Is my failover really happening after 60 seconds? Is my client really retrying? Is my client really supporting read-only mode? What happens if I lose a DNS or the DNS address or domain name of my database, or if I change it. Actually, back in the day, if you were using Java framework, you had to restart the whole framework to be able to update the DNS. There was no way to do a hot reload, all this kind of stuff. Right? And it was very common in old frameworks to do this, and many systems still are like this. And there's only in these conditions where you can actually test those. So try to experiment and think how chaos engineering can help you. And it's very simple chaos engineering. It's like vaccination. You go into the system and you inoculate with failures. The best one is latency. Latency is a deadly sin. It actually will take down system like you've never seen before. Add 300 milliseconds latency to a backend, and crazy things will happen. And in fact, I'll give you what we've noticed at Amazon, 100 milliseconds latency increase on the UI had an effect of 1% sale drop. 100 milliseconds is something the human eye can't even see, right? And through experiment chaos engineering, we realized actually 100 milliseconds latency increase on the UI has an effect on sales of 1% for each 100 millisecond increase, which is crazy. At the sale of Amazon, it's a lot of money. So this is a very good way to do it. But you don't necessarily have to do like applications or network or host failures. You can do people failure. I love the attack. Well, I call the Paul attack. We all have in our company a guy named Paul. Paul does everything. He knows everything, how things work, how they fix. He looks at the problem, fixes it, and we move on. You know Paul? You have a Paul, right? We all have those guys. Paul, give me your laptop. Don't come to work today. Superb attack. Actually, I've seen companies fail miserably because of that. And that's the bust factor, right? What if Paul actually dies today? What happens? How do we recover from that? Netflix does region attacks. Once a month, they actually break the entire AWS region and do traffic shift live in production while you watch your movie. That's how good they've become. They've been practicing chaos engineering for about 7-8 years. This is actually not impossible. It's something that you can also aim for. Start small. Don't necessarily go break a region right away. Start small and then build confidence again. And my last advice, actually, and this is totally related to resiliency, is always plan for the worst, but be prepared for the unexpected, because that's the unexpected that will break you. In fact, my last outage was a squirrel eating an electric cable. And that's how it happened. Right? So we never thought about that before. Okay? Thanks a lot, and thanks for staying here with me. If you want to read more about some of the stuff, I publish quite much on Medium, and that presentation is actually already downloadable. I just uploaded it to Speaker Deck, so if you want that, you can get it right away. Thank you very much. Have a good evening. Enjoy your beer.